All right, so today we're going to be looking at the similarities and differences between linear speed and rotational speed. Before we do though, we're going to review some things that we were learning recently. So, a torque is what causes an object to rotate or twist or turn or have an angular acceleration. Lots of different ways to kind of look at that. We usually look at rotate, twist, or turn though for this class. The next question we've got, if a 75 Newton force, so that is my force, is applied to a wrench that is 22 centimeters long. So we're going to go with, we're applying the force to the end of the wrench. So that is going to be our radius or our lever arm. And it is in centimeters, so I'm going to convert to meters and make that 22 cents or centimeters. Okay, so write it like you would after the conversion. And then what is the torque? We have our circle equation. Torque is on the top, and then force and the radius or lever arm are on the bottom. So if I cover up the Greek letter tau for torque, I realize I'm going to multiply the force times the lever arm. So in this case, 75 times 0.22. And of course, I didn't do this before I got started. So let's pause. All right, so we get 16 and a half, 16, there we go, and a half Newton meters for our torque. All right, so if you haven't already done so, you need to complete the rotational motion reading. So pause this and do that. And then we're going to take the notes. So you will want to find your notes packet. And in your notes packet, you want to find the page that says circular motion notes. All right, so the first thing that we're kind of looking at is just looking what an axis is. The axis is the straight line around which rotation takes place. So like you can think of it as your axle, same type of word. So the axle, that's your wheel, your tire, your bike wheel goes around. That is the axis of rotation for your bicycle tire, okay? Now we've got two different ways that we can do things. We can rotate or we can revolve. So a rotation is when an object turns about an internal axis. That is what you're filling in on your paper. When an object turns about an internal axis. So if I am an ice skater and I'm spinning around myself, like at the end of the performance, sometimes I do that, they spin around a circle. If I'm spinning around a point that's inside my body, then I am rotating or spinning. You can think of it that way. However, if an object turns about an external axis, it's a revolution. So the next one down you're going to fill in. A revolution is when an object turns about an external axis. So for example, if I run around if I pretend your track is circular instead of an ellipse type shape, okay? So if it's a circle and I'm running around the circle for the track, then I am revolving around that circle, okay? Because the point that I'm going around is not inside my body. It's some point. It's however far the radius is away from me, okay? All right, so let's look at some examples. Got a Ferris wheel here. The Ferris wheel turns about an axis. The Ferris wheel is rotating because it's an internal axis. There we go, rotates, okay? So the Ferris wheel is rotating. The riders on the Ferris wheel, however, are revolving, okay? So the Ferris wheel is rotating because here's my Ferris wheel, and this is a point, it's going around a point that's inside the Ferris wheel. However, the people are revolving because they're not spinning around a point that's inside of them. They're going around some point that's further away from them. Earth. Earth does both things. Earth revolves around the sun, but it also rotates around itself. Okay? So Earth is doing both things. So here's our sun, here's Earth. Earth is revolving around the sun, but then Earth is also here and it's just spinning around. So we see the sun in the daytime and then we're on the other side for nighttime. So it's spinning around like this as well. So it's doing both. It is rotating and revolving. So let's look at some of these other examples. Okay, we've got David. He's sitting on the outside edge of a merry-go-round. Okay, so he is. All right, so it is not inside of him. So he is revolving. Susan is spinning, so she is rotating because she's spinning around. The axis is inside of her. Jane is swinging a ball attached to a rope around a circle. I think we're going to say the ball. Let's say the ball. The ball is revolving. Jane's probably just standing there. A mound of clay is spinning on the potter's wheel. The clay... All right. A mound of clay is spinning on the potter's wheel. The clay is rotating because the clay is probably in the center of the wheel. 1 second. This is very annoying. All right, so we're going to look at rotational speed. This turntable, we've got down here, okay, it is rotating around an axis because of the points inside of it. However, this ladybug is revolving around the same axis, okay? Now, here's a question for the rotational speed. It's not letting me go to the next slide, sorry. All right, which part of the turntable moves faster? The outer part where the ladybug sits or a part near the orange center? That depends on whether you're talking about linear speed or rotational speed. So let's define them. Linear speed is the distance traveled per unit of time. So it's like meters per second, centimeters per second, miles per hour. Rotational speed, however, is the number of rotations per unit of time. So like 1 revolution per second or 5 revolutions per second. All right, so let's go ahead and look at linear speed. Linear speed is the distance traveled per unit time. So fill that in your notes, okay? So a point on the outer edge of the turntable travels at a greater distance than the one near the center. Therefore, the linear speed is greater on the outer edge. So if I'm on the outer edge, I might go like 6 meters to go around. If I'm closer, I might only go like 3 meters around. So if we're both going to go around, we're spinning together, so they both go around the same amount of time. This one has a greater linear speed because it's going more meters in the same amount of seconds. Sometimes the linear speed is also called the tangential speed. That's because the direction of your speed is always tangent to the circle. So if I'm right here, that is the direction that I'm going. Okay, so it's sometimes called the tangential speed. All right, let's look at rotational speed. Rotational speed is sometimes called the angular speed, and it is the number of rotations per unit time. Okay? All of the parts of the turntable rotate about the axes in the same amount of time. So all the little particles that make up this turntable, they're all going to go around in the same amount of time. However long it takes this one to go around, that's the same amount of time that it takes that one to go around. Okay? So they all do like 1 revolution per, if it took 1 second, 1 second. If it took 5 minutes, 1 revolution in 5 minutes. Okay? So, but they're all going at the same rotational speed. So all parts of the turntable rotate at the same rotational speed. A point farther away from the center travels a longer path, therefore it has a greater tangential speed, but they still both only went around once, Okay, so their rotational speed will be the same. Tangential speeds will be different. All points of the turntable rotate in the same rotational speed. A point farther away from the center travels a longer path in the same time and therefore has a greater tangential speed. A ladybug sitting twice as far moves twice as fast tangentially. So let's look at your paper. Ladybug A and Ladybug B, they have the same rotational speed. They're both just sitting here, and they're going to go around, and it's going to take them the same amount of time. So they're going to go the same number of rotations, so they have the same rotational speed. However, Ladybug A and Ladybug B have different linear speeds. Which ladybug has the greater linear speed? Ladybug B. So it might not be labeled. So this is A, this is B. Okay, this one has twice the speed. Why? Because it's twice as far away. So this would be the one that's going like 6 meters per second. This one only didn't have to go 6 meters. Let's say it only had to go 3 meters. So it would be going 3 meters per second if they go around once every second. Okay, so Ladybug B travels farther in the same amount of time, therefore, Ladybug B must have been going faster. Pause if you need to write all that down. All right, linear speed. We have 2 equations, one for linear speed, one for rotational speed. So on your paper, make sure you write down the circle equation for linear speed. It's the same as our speed equation from before, except we put linear here to remind ourselves that, hey, this object's actually going in a circle. It's spinning, it's going around in a circle, but we're just looking at how many meters it's going, okay, per second. So S is linear speed, D is distance, T is still time. All right, then rotational speed. We're going to say the number of revolutions or rotations, but I didn't want to have to write both words. So it's whichever one it is. It's the revolution or rotation, depending on what the object's doing. But it's how many times it goes around. This is the Greek letter omega, and it means rotational speed. And then T is time. All right, so if you need to, pause, make sure you get all that written down. We are next going to work on a worksheet. And we will do the first part of the worksheet together, but it's a different video. So you'll have to find the next video in order to watch it.